Alright, so back with classes. So classes are a way of packaging up in one type a bunch of data, like structs, and then operations on that data, like dot, hey point, negate yourself, hey point, go and add yourself to another point, scale yourself by some factor. And that's kind of cool, the ability to talk to something. This is called like message passing is the technical term across programming languages. So we're sending messages to these objects and they're responding to them. And that's so cool, right? So let's learn the right way to implement classes, because I did everything very lazy last time. I put everything in the class definition, but really a definition of a class is supposed to be where you define things, not where you implement them. So it was kind of lazy for me to give bodies to all these methods right here. Instead, you want to do it outside the class, right? So I implemented those methods inside the point class. It would be better to split up the declaration of the class and the implementation of the class. So a very common thing to do when you make a class is to have a header file and to then make a CPP file, okay? One with the definition of everything, and then the CPP file has the implementation of things, all right? You can even just split stuff up within the same file, but it's better to implement outside of the declaration, right? So let's get started with that. Let's put it all in one file, and then I'll split it in a second. I think that's a good strategy. So let's copy in our stuff from last time. What do we call it? Classes.cpp. I'll call this maybe point.cpp. Yeah, this is going to be the point class. So I'm calling it point.cpp now. And let's make it happen. So it's better to not implement these methods up here, but bring them outside. And just declare the fact that they exist up in the class. All right? So just say, hey, there's such a thing as a negate method. I'll give it to you in a second. Semicolon. Okay? I hope that makes sense. Something like that. And then same with scale and add. You declare that they exist, and then you implement them later. Alright, so that's how we're going to do it. Let's get these all pretty. Semicolon. Oh gosh. There. So these are now declarations, which is perfect. How do I want to say this? This is the declaration of the point class. Oh gosh. Let's do it this way. Declaration of the point class. It just says everything that's involved. It has the member variables, it has all the methods defined, and then you go and you implement those things outside the class. All right? That is the goal. Is that my sound still? I thought I muted myself. Who knows? But this is actually not going to compile right now. So like I brought everything outside, but that actually confused C++. So let's watch and see what the problem might look like. Point, -o point. This is not going to compile. It's like, what are you talking about? Like you're mentioning some variables. X doesn't exist on line 18. Yeah, it does. It's my member variable. But look at this. What does this look like if there was no point above? This just looks like a function, right? C++ thinks it's a function right now. We have not told it it's part of the point class. Okay, that's the key. So it's like, what are you talking about? I don't know about X. X is just a variable you have not given to me yet. So this looks like a normal function, and C++ thinks it is until you tell it. You need to tell C++ which class it belongs to, and then it's like, oh yes, I get it. This is a method on the point class. It's not an actual function all by itself. Okay. So this is what you do. You say the name of the function, really the name of the method is, it's part of the class. It's inside the class. So it's points, point, : negate method. So that's how you do it. Point, : negate. That's how you say it's a method. It's part of the point class, right? So this is the implementation of the point class. Does that make sense? This is how you tell it that, oh yes, this is a method. It's part of the point class, and then it understands that these X and Y member variables exist. So it's points add method. It's not just a function. It's points scale method. It's not just a function called scale. Now x and y, it's happy, and it will compile. Okay? And then everything works as it did before. Are there any questions about that? Yes?
Is there like an official term of what the colon represents? Or like?
Yes, it is the, oh gosh.
How would I read that?
It's an operator. It's like the access modifier operator. I forget exactly what it's called. C++ access operator. Something like that. Member access? No. I forget the name because I'm on the spot. C++ : operator. What is its name? Scope resolution. There we go. It's like you're going inside of something. You're going inside of the standard library. Something's defined in there. You are going inside of point. Something's defined in there. It's a new scope. Inner scope. Okay? Yeah.
So it's like you're accessing the scope of the class point, that scope, but outside of that scope.
That's exactly right. You got to be very specific, otherwise it looks like a function. Yeah, so this is what you do.
Could you, in theory, outside of the class, outside of the function, just put point x or point : x, and then that would access the points x?
I see where you're going with that, but that's just not where you declare those things. If you just want a normal member variable, the declaration goes in the class declaration. Yeah. This is talking about something that already exists. It's not creating it. Yeah, that's a good question. Any other questions? So, if this makes sense, let's split it up. Let's split this up into a header file and a CBP file, and then even like a main file. But we split it up within the same file right now. Let's do it even more. But as I like you to do, read that scope resolution operator as ''s. It's points negate method that we're going at and implementing. So, all right, I need point.h. Remember your header file guards. Oops. And there is where we will place the declaration of the point class. That's where it's going to live. Declaration lives here, and I can delete it from here. That's the declaration of the point class lives there. And then we're going to place the implementation in point.cpp, so it's happy right there. And then I'll make even a further file like with a main function. We'll do it main.cpp. That's what we've been doing anyway. So let's do all this. Oops, not that file, this file. Then we'll bring the main function as well into that main.cpp file. And so we want to use the point class as our little point library. Include point.h. And now suddenly it knows about all these things, assuming I saved the header file. So now it knows about the class. And then in the implementation file, you need to include your class declaration, otherwise it doesn't know what you're talking about. So this is one of those times where you are kind of forced. When you're implementing classes, you are always forced to include your header file. Otherwise, it's like, what is the point class? So this is the right way to do it. All right, implementation of the point class goes here. The declaration of it goes in the header file. And yeah, the use of the library can go in like your main.cpp file. Include it, start doing stuff. All right, and so to compile, it would have been something like G++, and then all of the names of our implementation file. So G++ main.cpp, point.cpp, -o like point. Whatever we want to call it. And nothing has changed, right? So again, we have the implementation of the library, of the class. We have the header file that defines the class that exists. And then the use of it in the main file. It starts talking about points, right? They're all coming together. Any questions about that? Okay, so I have promised you the opposite of public. So let's talk about it. So private is, of course, the opposite of public. It lets you control the access to your class, to pieces of your class. So by saying public all over the place, we gave complete access to everything outside of our class to the user, okay? So everything after public is visible to the user outside of the implementation. So, for example, because X and Y are public fields, public member variables, I'm allowed to mess with them in main, somewhere outside of the class implementation. So like over here, like point P, and then I can start asking about P.X, 42. Because it's public, that means it's accessible, this line. X is a public thing, so it's accessible. And then also negate. That was a public method, so I'm able to call it outside the class, right? It was a public method, I'm able to use it like that, okay? Some things you don't want to make public. A lot of the time you do not want to make your member variables public, all right? Because you don't want the user to be able to mess with some of those pieces, right? So we'll mark those special things private, and that will make it so that the user cannot even try to do this. It will be a compiler error, right? That's going to be the goal. But before we get there, let's do some testing. Let's test our point class to just get some experience with that. It's good practice. So remember what it means to make a test. You're going to make a little baby program, and you have a scenario in mind. You're checking some piece of it, like a few methods, and what you do is you run the program in your mind, right? You know what the answer should have been, and then that will tell you what to expect. You're going to compare with assert true or like an if statement whether what actually happened in code, what you're getting back from your methods, is exactly what you expected to see happen. All right? So let's make some tests for like negate and scale. So for example, so it's always compare what you got with what you expected. That is the key. So yeah, let's make a negate test and a scale test. Let's be like, I don't know, point P. Here's a test. Let's say that we have a point. We got to make one. And then let's set its X and Y so that it's normal values, not garbage. 42, 43. And then let's call P.negate. That's a test. Or it's the first part of a test. What should have happened, right? We have to run the code in our minds. What do we expect to see happen here? If this was 42 and this was 43, then after calling negate, we better see an X, negative 42. We better see in Y, negative 43. And that's what we're going to check for. Does that make sense? That's going to be our test. Let's do that. So, instead of having a main function, I will comment out all of this. We're going to make some tests instead. And so up here, maybe we'll make a test negate and a test scale. And we'll just make them as functions. That's a normal thing to do. Test negate, test scale, and then we'll make some bodies for those testing functions. So they'll both be void. Just do their thing. Call assert true. I need to include the definition of assert true. So let me steal that from someone. Where do we have it? Lecture 13, maybe? Count words, I think we did a test, right? Count words main.cpp. Oh yeah, there's an assert true. Let's steal that. And it's using a strings as a parameter, so I gotta include the string library. And so, all right, test negate. Let's do exactly what we just said. We're gonna make a point P. P.x equals 42. P.y equals 43. I'm going to call P.negate. What should have happened? Assert true. What should have happened? Well, P.x better now be negative 42. Yeah? P.x better be negative 42 now after that call. And P.y better be negative 43. That's what we need to check. So I can call this, I don't know, negate. Give some description. All right, and that'll be our test. Any questions about why that's going to test exactly what we wanted here? We set up a scenario, and this is what should have happened. Let's do the same for scale. Let's see here. Yeah, let's do one for scale. Let's be like, I don't know, point Q. Q.x equals, let's use, they are doubles. Let's use doubles. 2.5. Q.y, 3.5. And then let's scale it. by 2, or a factor of 2.0, because it is a double factor. And then what should have happened to Q? Assert true. Well, Q's x better now be double what it was, so 5. Again, this is one of those do as I say, not as I do moments. I know that it's going to work if I compare doubles right now for exactly 5, but you should never do that until you have a computer science degree. So 5.0 will work this time, but it won't usually. And Q.Y better have also been 7. Okay? But you should have used like subtraction and absolute value. Remember that. This is a scale test. And so I'm calling both of these in main. And that's what should have happened. Let's see if they do happen. Remember to give both of your implementation files to G++. And cool. We got them both passing. Nice. Any questions about that writing tests? Because now I want to go back to let's see. I want to get to privacy in just a second. But there's a reason, there's a reason somebody came up with this idea, right? Public versus private. There's also a third thing that we might touch on later in the class. You'll at least read about it. It's more of a 41 topic. But what the difference is, the reason you might want to hide stuff from the user, again, you don't trust them, it makes it easier to reason about your class, all right? This is a philosophy slide. It enables something called information hiding as well as encapsulation. All right, so these are two very important words in object-oriented programming I want you to know. So encapsulation is when you are bundling your data with methods that operate on it. That's just having classes in a nutshell. Just by having classes, you're encapsulating things. So every point object that you make, you think of it as, essentially, it has its own X, it has its own Y, yeah, but you also think of it as having its own little version of scale that operates on it. Oops, not scale, scale. It has its own version of negate that operates on it. It has its own version of add that operates on it. Stuff like that. So you're bundling data with methods that operate on the data. So you think of it as like points not holding just their data, but also they hold their special versions of each of their methods. Something like that. So that's encapsulation. That bundling idea. It's nice to have it all in one place, I think we've seen. That's the fancy term for that. And then public versus private gives us access to this idea of information hiding, where we're only letting the user see just enough, just what they want, just what we want them to see as the implementers of the class. Just enough for them to use it and be done with it and not mess up too much. So we only give them access to the public stuff. Everything that we make private is just for us, the implementers. As implementers, we get to see everything, of course. But public stuff is what we get the user to see. It's what we give to them. So the whole point of making some things public and some things private, again, I haven't given you code for this yet, but I will show you soon. The whole point of that is that you can change stuff. As long as you keep the pieces that the user has access to working the same, you can mess with everything else. You can go and implement, you can go rename your member variables if you don't give the user access to them. You can go make a better version of all of your methods. As long as whatever you kept public still works in the same way, the user is going to be none the wiser, and they're not going to yell at you. Go make it better. That's the goal. That's what information hiding is all about. Just give the user access to the bare minimum that they need to do the thing, to use your class. Everything else you keep to yourself. Right? This will make more sense with more examples, I think. But just by the way, pretty much all of the C++ standard library types that we've been using, those are secretly classes. So string, it's initialized in an interesting looking way, but all it is, every S object it's a class, right? Every string object is an object. And .at, you've been running methods, right? And what else? Vectors, of course. Those are classes too. They have .size, .pushback. Those are methods on a vector object, okay? It's all there. Everybody loves object-oriented programming. It's happy, all right? So I think we are ready for public and private. Are we ready? An example in code of public versus private, because that's going to force us to do some things. So we have to mentally prepare ourselves. Okay. So key idea 1. We should never give the user access to the member variables. We should never let the user do what we've been doing. We should never let them say p.x equals something or access immediately p.x. No. No, thank you. Because what if your class uses its member variable in a special way? Like, what if the value of your member variable is always supposed to be positive, your x member variable? The second you give the user access to it, they can totally go and make it negative behind your back, can't they? And that ruins your entire class. So don't give them access to it like this, because then they can go and update it. We don't like that. So never give the user access to your member variables. That is a very common thing to do. Instead, they got to go through a method, p.setX or something, set x to 42. The second you let users go through a method to set the member variables, or to even get them back, then you can start putting if statements. If they ask to give you negative things, you can be like, no, I'm not going to take your value. See how you have control the second you start doing that? That's better. All right, that's our goal. It's like, what if your points? You only want your points to be in the positive, like the first quadrant. X and Y should be positive. You can't let the user set the X and the Y, because they might make some negative. So the second we start restricting this access to member variables, that's a very common thing that you want to restrict access to. Watch what happens. We've been using them all over the place. So here's the public stuff still. How do I want to explain this? Like everything that's public is accessible to the user. All right. So I'm going to keep these methods accessible to the user. That's fine. But I'm going to start making these member variables private. So these cannot be accessed by the user. Accessed. Cannot be accessed by the user. Now, all right. So everywhere I said, I made a point and accessed its X field or accessed its Y member variable. Now it's not going to compile. Watch. And that's what we want. It's like, it's a lot of errors. It's like, all right, main.cdp, p.x equals 42. Sorry, X is private. Y is private. Cannot use them. All right? So the second you do that, how do you set X? How do you set Y? How do you get the value back? Right? Once you start restricting this access to your member variables, which you should do, you have to add public methods to get them back and to mess with them. Right? So those are called getters and setters. So you're going to make a getX method, a getY method. That those are called getters or accessors that give back the value of your member variable. Maybe computing it on the fly if you're not actually saving it. And then you're going to have setters as well. That take this new thing that you want to place into X, and you have the opportunity now that it's a method to maybe look at the value the user wants to set in and make sure they adhere to whatever we're trying to make it adhere to. All right, any rules, we can keep track of that in these setters, also called mutators. All right, so a getter method gives back the value of a private member variable, and a setter method sets the value of a private member variable. All right, that lets you have control, better control. Don't let the user just do what they want to your member variables. That might ruin some rules that you have in your class and in your head. All right, so let's do that. We got to make some setters and getters. So let's make it how we want to make it first. Like, what do we got to do? So instead of this, p.x equals 42. Cannot have that anymore. Same with p.y equals 43. Can't have that. What we can do, what we need to do is be like p.setx and give it 42 and have that method do it for us. Okay? p.sety 43. That will work. And then if we want to look at the value at the end, watch it, hope that it's changed, we're going to use a getter for that. Get X. That better give back 42. Get Y. Give back negative 43. Negative 42. All right? So that's how we got to do it. So it's q.setx to 2.5. This is giving us some nice fine-grained control over variables. Set Y to 3.5. q.getX. Better give back 5. q.get the value of our Y member variable. Better give back 7. All right? So that's pretty nice. So let's go and implement those now. First, we have to declare that they exist in the header file. So we have to say get x and get y. Those are both methods that give back the value of our member variable, and those are doubles, so their return type is double. Double, those are our getters. And then we have setters. So they're going to take the new thing that we want, like we want to set x to some new double value d. And it's just going to be a void method because it just goes off and it messes with our object. Right? Set x to some new value d. Set y to some new value d. Right? So that's how those are going to look in the declaration, and the implementation is going to be as you would expect. All right, so let's go to the implementation file. Put them, I don't know, put them down here. Getters and setters. Let me make some bodies for all these. And then we'll put stuff in them. All right, so what should getX do? Just give back the value of our member variable. It's very easy for this implementation, but you could imagine that for a class, it's going to be fancier. And by the way, this looks like a function right now. It's really the getX method on the point class. So it's always point colon colon. Got to do that all over the place. That's how it knows that x exists. So return y. Okay. So you could also do some computation here if you needed to. There was something weird you needed to do with your member variables, and now you're able to do it, rather than just giving them to the user verbatim. And then set x should be like, all right, set the x member variable to whatever d was, set the y member variable to whatever d was. The implementation is as you would expect. And then everything else is the same, right? Now, in main, I'm saying set x and set y. It's happy. It knows about these things. It's getting them back to this is better. Better access control, and our tests still pass. Are there any questions about that? So that is information hiding. That's an example of it. And getters and setters give us control over what kind of information we want to give back to the user, what kind of things we want to take from them. All right, so that's fun. There's some other fun, interesting ideas as part of class implementations. What else? Let's talk about const. So, oh man, I'm so sorry. There's like 3 different things that const means in C++. Here's a third. So if you put const at the end, if you put it at the end of your method, not as a parameter, it's in a weird spot, then it's going to make it so that you are unable to modify your member variables, any of them, inside of the body. All right, so let's talk about this. So there's so many different things that const does. So first, you can make a const variable that you can't change. We've also talked about parameters that are const. So like if you do this, that means you're passing along a string that you can't touch. You can look at its characters, but you can't touch it because it was marked as const. You can't mess with the characters, but you can retrieve them. That's fine. There's an equivalent for classes when you have a method and you don't want it to be able to touch any of its private member variables. Like it would have been a mistake to do that, so let's enforce the fact that we cannot do it. All right. To do that, you put const after the method. All right. To make this happen. And this is super nice, right? Sometimes there are some methods that you don't want to have messing with your member variables, like set x and set y. Obviously, they're messing with member variables, but like get x and get y, there's no need for those to ever change x or y, right? So those are good candidates for const. That's the idea. And so that's really helpful when you test, because now you have fewer things to test. Now you know that it's never going to change if you mark it as const. You can be very confident that it won't touch its member variables, right? So getters are a great example of things that should always be const. And here's how you declare that fact. Here's where you put the const. It's a new weird place. So in the declaration or the implementation, you say, like, here's the original. It's like double get x semicolon. Here's where you put the const. You put it after. And this marks the entire method as const. Semicolon. Yeah. Oh, that's the slowest thing I've ever. That's weird. Must be an internet problem. Thank you. Is it working now? No, it's still very slow. It just sped back up. Let's see. Is it happy again? Huh. We'll see if it catches up, but thank you. I think I have one way to fix it, maybe. Just plug in the HDMI cable. It'll be a stretch, though. But okay, this is how you do it. Double get x const. All right, that's where you put the const. You mark it as a constant method. And so get x is now, you say it like this, a const method. Yeah. All right, so let's do this and watch it enforce some stuff for us. You do this, you put this const in the declaration and the implementation, by the way. So let's go to let's go to the declaration first. And so every getter should totally be const. What else? We'll figure this out together. Yeah. Because it's not changing anything. So you put it there, and then you also put it in the implementation. So it's got to be get x const. You put it after the parameters and then before the curly brace. It's really weird. So that's where you do it in both of those places, and just like that in both places. And that enforces the fact that you can't change your member variables. Nothing as far as execution changes. Like we aren't messing with those member variables in those methods. But if we did accidentally try, it's going to make sure we cannot. So like if here we tried to say, oh yeah, get y, before you give back the value of y, that should always set the y member variable to 42 or something weird like that. This will not even compile now, just like for normal constants. Every single member variable is marked as read-only the second you do this. Assignment of member variable point y. It's read-only.
And if you were to say int get y, x equals 42, that would compile it.
That's right. Every single member variable at once. Every single one of them is marked as read-only in a const method. Neither of these lines will compile. Whee. It's still not loading very fast. I can't explain that. That's weird. Let me try disconnecting and reconnecting, but after I explain this. So here it's saying like read-only object. It marks the object as read-only for a split second when all this happens. Right? That is the goal. And yeah, I did that highlighting like 10 seconds ago. So let me fix the screen. Let's see if just disconnecting and reconnecting will fix it first. That would be nice. But if that doesn't do it, then we'll have to pull out the big guns. Moment of truth. Sorry about that. The classroom is haunted after all. Oh, you guys know we're going to get a Friday the 13th in October? That's going to be great. That's the right month for it. And it's trying to connect. It's thinking about it. Is it giving up? That's so confusing. Alright, I'll give it another few seconds, and if it still is unhappy, here's what we can do. I don't think this is going to reach, but maybe if I pull on it, it will. Alright, yeah, this projector, it's just extra unhappy today. Sorry about that. Let's do this. Cool. Alright, should be happy for the rest of the lecture. At least it updates faster with the cable anyway. So, alright, where were we? Const. There are more. Are there any other methods that should not be allowed to mess with member variables? These are the other ones. Do any of those count? Do we see that any of those might be able to be marked as const? Yeah, so negate, definitely, it's messing with its member variables. Can't do that. Scale, also messing with the member variables. But add, is add messing with our x or our y? No. It's making a new point and messing with its x and y, but that's not us. So that's fine to want to change the values of something that you're giving back. This is not your current object. We're just accessing our X field and our Y field to do some computation. That doesn't mean we can't do it to some other point. So that's perfect. So add is another candidate for const. And so we can do this. Mark it as const here and here. And that makes it so that we can't mess with anything. All right, so same with all these. And so I got to comment these out. Whee. So this should not be allowed. We don't want that to be allowed. There. But now it will compile and it will run. Oh shoot, what have I said wrong? Did I not save one? Oh, I didn't save the header file. Sorry. Passed. Yeah.
So wait, if add is a point type, right? So or it's
going to return a brand new point.
So and then within the add function, you're making a result point.
Yes, I'm making a new point.
So wouldn't like result.x and result.y not work?
No. It totally works because that's not me. That's somebody else. What const means is you can't touch your own member variables. That's my X and my Y.
No, I mean like because you made them private.
Oh, I see, yes. Private is talking about when the user wants to use our stuff, like in main. That's outside the implementation of the point class. But here we are inside the implementation of the point class. We have total access.
You're in the scope of the class.
Yeah, we are implementing it. This is a method of the class. We have complete access to everything. Because we're the implementers. We get that access. We get that power. Yeah. Public and private mean nothing when you're inside the class. Only outside.
You are outside the scope of the class, such as in main or in a completely different like class or function or whatever, you could do that.
Yes, you got it.
That makes a lot of sense.
Any other questions? These are good ones. Yeah, const is nice. Keeps you from hurting yourself too badly. Here are some questions for you. You can just do this on your own, but I think I have a couple questions for us. This will be fun. So here's question number 1. Get in some groups and work together on it. Please take this class definition and I don't know where you want to do it, but just like in your head or write it down somewhere. I don't have to look at it, but take some time to discuss how would you change this according to all the things that we talked about, all the guidelines I talked about today. What would you do? I can think of at least 2 things that should change here or should be modified in a certain way, right? So give that a try. This is the blah class. It's got a member variable and 2 methods that do what you would probably expect them to do. How would you change it according to the best practices that we just talked about? So take a couple minutes to discuss. Let's see. All right. I think our voices are dying down now. Is that enough time? What's one thing that somebody noticed that should change? Yeah. Nice. Yeah, so every member variable should always be private. We don't want to give the user access to it. That's one thing. Anybody else? Give me another one that they saw. So we just force the user to go through the setx, right? b.setx to 42. Rather than being like b.x equals 42. They no longer have that ability by making the x member variable private, which is great, right? And then there's one last thing, at least that I saw. It's that this getter, right? This getter should be const. It should not be allowed to change its member variables, and we should mark it as such, right? That's the idea. And so, yeah, we're going to force the setter to set b's x to 42. That's the goal, right? Does that make sense? Those are the two things that are best practices that we've talked about today. All right. With that, I have one last question. And it has to do with an error that is so common. It's so common among 40 students. It's still very common among 41 students. My 41 students are doing this all the time. All right. So here is an example method. It can't be const because it's going to change things. Let's make a reset method on points for some reason. Let's have it reset the x and y to 0. That's what it's supposed to do. All right. But right now, the reset method is doing something horribly wrong. And I do want to see your answer this time, so please go to the written nice page. Let's take a look. And please do attendance. I will stop that soon. So it is, let's go to the written nice page. I'll clear it out. But there's something horribly wrong with this implementation right now of this reset method. Why? What do you see? Can you find it? What is the problem? Write down it as much as you can figure out. Meant to zero out the x and y fields, but for some reason it's not. Compare this implementation to other methods that I've already written that do similar meshing with things. There's a subtle difference. And this is so easy to mess up. This is why I'm telling you about it. You're gonna mess it up. You're gonna do this. Was that enough time? I guess you either see it or you don't. Let's see if anybody saw it. Oh yeah! Good job, those of you who found it. There's an issue with x and y variables. We're making brand new ones. Dun dun dun. It doesn't have to do with const. This answer has to do with const, but we're not marking it as const. So we do want to modify the member variables. And we are inside the class. We're actually doing it. So this is a method. It should be loud, but it's not going to do it. So 33 and 34, good job. Declaring new variables. And this is such a common error. You're going to do it. It happens all the time. You're going to do it next semester too. But let's figure this out, all right? Let me try and explain this. Let's make this method. Let's make this reset method. How do I want to do it? This is from the crushed ice. Right here is void reset. No parameters. And so let's go over here and implement it. Way down here. And here was the original implementation. It was void points reset method. We're going to say double x equals 0, double y equals 0. Do you see the difference between that and like a setter? See the problem already? Like, these are setting x and y member variables. They're doing it right. These are not setting x and y member variables. You see the addition that shouldn't be there? So let's watch it mess up with maybe a test. Let's go to the main file. And I'll make a test reset function. Why not? Let's go there. Let's make a test reset. I'll use this one. So here is my test scale. I'll just copy and paste it into a test reset. So set the x and y to the same thing. That's fine. And then run reset on Q. So Q's x should now be 0, and its y should also be 0. Reset. Okay, so that is a test. It's not going to work right now. It's not going to pass. It'll compile to run. It's a bug, yeah. It's a logic error. Very subtle. So it fails. All right. If it's not 0 and 0, what is it then? We can print it out. Cout q.getx. We just called reset, though. It should have done something. Not get, but get x. And then q get y. All right. If it's not 0 and 0, what is it then? We can print it out. We can modify a test. That's fine. It's still 2.5 and 3.5. Nothing has changed. Weird. All right, let's talk about this. So what's going on in this code is, let's see, should I draw it first? Yeah, I'm going to draw it first. Let me draw a stack diagram. So here we were in main, way on the bottom. Tiny main. Main was calling test reset. Test reset. All right. And then test reset made a Q object that had an x and y holding 2.5 and 3.5. X was 2.5 and y was 3.5. Sure. And then we called the reset method on Q, q.reset. So let me draw everything that the method knows about in green. So the second you do this, you go up here, and you call the reset method on Q. And so if you were to right now talk about x, you'd be getting Q's x and Q's y. So it's right, it's correct the second you hit the body. But watch what the body does. The body makes a brand new variable. When you say double, when you put a type somewhere, you made a brand new variable for yourself. Does that make sense? There's a brand new local variable called x, local to the method. Brand new variable called y, local to the method. Sets that to 0. That's fine. But that did not do anything to the object's x and y fields because we just shadowed them with local variables. Those took priority. Does that make sense? So these lines, look at how set x and set y are doing it, and look at how reset's doing it. When you say the type, you've just made a brand new variable, right? That's not what we wanted. So the following code creates new local variables called x and y. They shadow the other ones. Shadow the x and y member variables. And that is not what we wanted. Sad face. Question.
What if you made like a new variable, just say like double A, in that point you wanted to access that in, say, main or something?
No, you don't get it. Just can't do it. It's a local variable, just like it's just a scoping problem, just like any other function. When that function returns,
not even with the colon.
Then you'd make it a member variable, though. So you'd have the same problem either way. But yeah, a function returns, all of its local variables go away, and this is where we're making local variables. Yeah, so can't do that. Instead, just talk about the member variable that already exists. That's what you should have been doing. All right, set x. Don't need to declare it again. Set x to 0, set y to 0. That's actually going to touch the member variables now. Does that make sense? That's how that's going to work, and now the test will pass. But yeah, this reset method returns those x and y local variables. They went away, and we never modified the original thing with that incorrect implementation, right? And this is the world's most common error to make in object-oriented programming. You're going to make it a lot. My CSCI 41 students make it a lot still. It's going to happen. So now, if your member variables are not changing properly, this should be the first thing you look into. Okay? I think that's all that I have to say about that. Any last questions on any of that? Alright, so that's where we're going to stop for the lecture today. Let me release your next lab, and then also I want to do this feedback thing. So, step 1, lab. There's usually a little button here. Where did it go? There it goes. Maybe I just have very slow internet on this laptop, and that's why it was having trouble. Alright, so this lab is about functions written across files. Alright, so practice with functions finally, making our own. This one is all about rational numbers. Alright, so rational numbers. This is just a mathematical pretentious way of saying fraction. We're going to make programs that work on fractions. Alright, and how to do some calculations on them. Okay, so let's go to the, well, I guess first, before we talk about code, a rational number is a fraction. It's just any number that looks like a over b, where a and b are integers. So technically, whole numbers are rational numbers, because like the number 42 is 42 over 1. You could make it a rational number, but it just means fraction. All right, so we're going to work with fractions. We're going to work with fractions for this lab, aka rational numbers. And like every human, we like to... I think all of us prefer fractions in simplified form, right? Instead of saying 2 over 4, we should be using 1/2 everywhere. So we're going to write our fractions in a way that they can be simplified, and we're going to write a simplification function, right? So yeah, multiplication is easy on fractions, addition is hard, so we'll wait on addition for later. I'm going to ask you to write a multiplication on fractions function now. But here's the code. Let's look at it. Start code 4005, I think. Yeah. All right. So here are the files that you get, and I would like you to first implement rational.cpp. You're going to implement it's a rational number library. You're going to implement all the functions in rationals.h. All right. So let's look at the header file, rationals.h. Here are all the things that we're going to be working on for rational numbers, right? A way to take a fraction, that's a numerator and a denominator together, and create a string form of it, so that's all pretty. You can print it out later. So convert a rational number into a pretty looking string that's all simplified and nice, with a slash and everything. And then here are some other functions. A function to multiply two rational numbers, rational times. It takes two rational numbers. It takes the numerator and the denominator of the first rational number, the numerator and the denominator of the second rational number, and we are giving back, we're returning the answer with reference parameters, because we need to give back two things, right? So we're going to use an int reference for the result numerator and an int reference for the result denominator, and your body of this function is going to mess with these values, setting them to the appropriate thing, also simplified, right? Making it fancy and nice. So that's your times, and then these other two functions will be calling this one to help it out. This is rational simplify. It takes a fraction by reference, the numerator and the denominator as two separate arguments, and it's going to change them to become simplified, right? So if this was 2 and this was 4, it would change it to be 1 and 2, right? Because 2/4 should simplify to 1/2, yeah? Etc., etc. Any questions about that so far? So rational numbers are going to be passed as two things, the numerator and the denominator of this fraction. That's the first bit. Yeah, so, yeah, that's going to be what you're implementing, and you're going to implement it in rationals.cpp. So here's the CPP file that you're going to be messing with. The header file you don't touch. Oh, sorry. Rationals.cpp. So I've given you a helper function called GCD, right? The greatest common divisor. This is going to help with simplification. Just for us, we don't need to put in the header file. So simplification works like this. There's some cases you gotta mess with, but just notice, first of all, that rational simplify and rational times, they don't give back anything. They're void functions, but they're still going to change values because they're taking those values by reference. Rational simplify is doing that. Rational times also void, but it's messing with the fraction by having reference parameters. Okay? That's the key. They will automatically get changed thanks to call by reference. All right, let's see what else. All right, so yeah, let's start talking about how to simplify stuff. So the simplification function should work like this. There's going to be several options that you have to watch out for, but let's just do the default option. You have to keep track of whether it's negative or not for a reason, but let me draw some stuff. Boink. So this is information about your lab. All right, so if you are given the fraction 2/4, right, you need to simplify that. Your simplify function needs to end up changing the numerator to 1 and the denominator to 2, yes? So this needs to get transformed into 1/2. That is the simplified version of it. And so you have to discover that you need to divide by 2, all right? The way to discover that you need to divide by 2 is to give the numerator and the denominator to the GCD function. The greatest common divisor is what you should use to simplify. Does that make sense? It's the biggest thing that can divide them. GCD, if you call that function, I made it for you already up here. You just call that on 2 and 4, your numerator and your denominator, it will give you back 2. Yeah, 2 is the greatest number that divides into both. And so that's exactly what you need to use to simplify your fraction. Does that make sense? That's how you do it. You do need to watch out for negatives because the GCD algorithm only works with positive numbers. So you have to remove any negatives with the absolute value function. And so there's a few cases, right? So the very first thing you do is figure out if this rational number is negative and you save that away in like a Boolean variable somewhere, right? So it could be negative in any of these ways, right? If the numerator is negative and the denominator is positive, non-zero, then it's negative, right? Because one side's negative, the other is not. And then if the numerator is positive or 0 and the denominator is negative, then it is negative again. I guess technically you don't need the 0 part, but it doesn't matter. So again, if one side is negative and the other is not, that means it's negative. If neither of those are true, then it's either a positive over a positive or a negative over a negative. Either case, still positive. Yeah. So figure out which case you're in, figure out if your rational number is negative or not, and then save that for later. And make all of numerator and denominator positive. Use absolute values so that you can give them to GCD. GCD needs positive numbers, right? So like if you were given -1/2, you like save away that, oh yeah, that's negative. But like if it was -1/2, it's positive. If you were given 4/8, like change it so that like it's just 4 and 8 right now. So you can give that to GCD, all right? That's negative. So convert them to positive so that you can use GCD, and then I want you to simplify the numerator and the denominator using that GCD. So divide them by whatever, so like 4 over negative 8. If you make it both positive, right, then just save that as negative for later. You divide by 4, right, because the GCD of 4 and positive 8 is 4, so you get 1/2 again. And then you need to bring back the negative in. If it was negative, negate the numer. That's how we're going to do it. Right? So the numerator is going to be the negative part if the thing should be negative. That's what normal looking fractions look like, right? The numerator is the negative thing, not the denominator. Okay? So that is how you implement rational simplify. And you're just messing with these values, so once you change them, you're done. You don't return anything. Technically, you are returning something by messing with the values. Okay? Any questions about that? So you're using the GCD function after you make sure everything's nice and positive. All right, so that's the first part. Next part, I guess rational times takes two numbers, one fraction, another fraction, and you give back the result by messing with these variables. Somebody else made them for you, you're just going to change them, all right? So they're reference variables, reference parameters. I do want you to simplify your answer. Call rational simplify on the answer before you're done with this function. Because usually when you multiply fractions, it can be very easily simplified, right? But in general, if you have two fractions, a over b and c over d, and you're multiplying them, the answer is, right, ac over bd, and very, very often this can be simplified. So simplify it before you give it back, all right? So that's the rational times function. We good with that one? So call simplify. And then the last one is rational pretty string. So you're going to give back a string form of your value, okay? There is, by the way, a toString function in the string library that I've already included for you up here that you can use for this. It takes a single value, like an int, and it creates a string out of it. So if you call the string library's toString function, toString, on an int, on like 42, it will give you back the string 42. That's perfect because you're going to build up a string that looks like the fraction. So your goal for pretty string is to take a fraction, simplify it, call simplify, and then extract pieces, right? So, for example, here's what you should be giving back. Like if the numerator is 2 and the denominator is negative 44, so simplify, the fraction is negative 1 over 22, so you're going to do that simplification. Then the string you should give back, you're not printing anything, you're giving back a string. The string you should give back is negative 1 space slash space 22. So it's just, you make it pretty. Make the fraction look pretty, okay? And if the numerator was 2 and the denominator was 4, then the final string you should give back is 1 space slash space 2, okay? That's just how I want you to do it. So simplify before you do it, and everything should be happy. Use toString to take your individual numerator and your denominator into a string form. And then you can like put some spaces and a slash. Okay? I think that's all that I wanted to talk about. Any questions about any of those functions? That's going to be the bulk of your work. All right? Remember, you're giving back a string in that function, not printing anything out. So I've made a little sample file for you that you're not turning in. This is just to help you get it right and to test things out. So here's a sample program that like asks you for fractions, and it's going to run your code for you, but you're not turning it in. Instead, we're going to write tests. So for this one, this is just a sample file that's including your library and like asking for numerators and denominators and calling all the functions that you've written in the way that you can. So like here it's simplifying, it's multiplying into some result variables, it's outputting the result as a pretty string. So it's running everything that you would implement. And so for example, with these exact input values, you should see these exact output values. So that's a way to get it working before you're ready to do the full-blown test file that I gave you, right? That's just a helper file for you. Get that compiling and running. Remember that you have to compile it with your library. Give that main function file plus the rationals.cpp file where you implemented your library. All right? And then finally, I made tests. I made you a test.cpp file. This is what you're going to be graded on. The other file is just for you to get it working. Test.cpp. That's including your library, and I've made some unit tests for these functions. So here's a simplify unit test. This is what should have happened to numer 1 and enum 1. That's variables. Here's a times test. It's multiplying these. This is what should have happened. We should have seen those values. And then pretty string. We should have seen this final output. That should have been the result string. Okay? So those are my tests. Get those passing. Compile and run like this. Give the library as well. Once you get those passing, there's a reason that this is going to be due October 13th, so you get 2 weeks to do it. Because I want you to write tests too, right? So once you get the library implemented, my tests passing, it's your turn to write tests. Where was I? To be extra confident, I want you to write 2 more tests in my style, all right? Add them to the end of the main function, just like this. So you're going to write, here I am declaring them, here I am implementing each test, calling assert true once per test. Your turn. Make 2 of them. 2 tests, make some scenarios in your mind, 2 separate ones, and then figure out what should have happened, like call some complicated like combination of simplify and times and pretty string, whatever. Make 2 tests, each should call assert true just once, and you can test whatever you like, right? It could be about anything. Maybe you can test that like calling simplify twice doesn't change it, something like that. That's not something I'm testing right now. Maybe you could do that. So come up with your scenario, write 2 more tests, and so I should see passed. The autograder is looking for passed 5 times, right? 3 from my tests, and 2 from yours. And so you can follow this pattern, but make yours fancy and test new things. Any questions about any of that? So there's a reason why it's a 2-week lab, definitely. There's a few pieces, but they all come together, I think. All right, and so you're going to be turning in the files that you mess with, rationals.cpp, the implementation of the library, as well as test.cpp, where you wrote your tests. Okay. Notice that you're not turning in rationals.h, so you may not modify the .h file. You cannot change the header file. That is set in stone. Right? That is, I think, everything. We're good with the lab? Rational numbers, fractions? All right. So the last piece is this mid-semester anonymous feedback thing. So we're week 8. There's like, I don't know, 18, 17 weeks of class. I can't even remember. We're about in the middle. And that survey that they gave you last time, I don't get to see your responses until the end of the semester and like grades are due, right? So you could say bad things about me. I would not know. That's the whole point of that. If you would like to give me feedback, though, that like I can still see before the end of the semester, like if there's something going wrong and like we could change it, let's tell me about it, right? So here's a little Google form. This is, of course, not required because it's anonymous. But if you would like, please fill this in with as much or as little information. I would appreciate your feedback. Give me 3 things I should keep doing, stop doing, start doing, blah, blah, blah. So, yeah, if you have something to say, please say it while maybe there's still time to make a change if there's something going wrong. Yeah, so that is my feedback little page. Please do that if you're interested. I would appreciate it. Yeah, I think that's everything. Are there any questions about anything we talked about? So I think finally we've gotten through everything. So yeah, the rest of the time is all yours to work and ask questions.